cool. Yeah, let's see if that works now. Playing with the settings a little bit again with OBS, but yeah. So where are we at? What I wanted to do today is I wanted to code the control gate at least for the 2-qubit case, and maybe we'll start taking a look at a way to represent those things, to print them as actual graphs maybe, and then eventually get to hypergraphs. But first we'll just stick to graphs and see if we can just implement the whole thing for graphs first, and then we'll see how this changes when we go like to 3 qubits and up. So to apply a control gate, right? That's how do we do this, right? So to apply a gate, I'm assuming that's correct. I don't know. And that would be important to state vector would be also good to do because it will allow me to actually run some tests. That's an important thing to do. So, but to apply the control gate, so what will we do? So, do we need to do the, we need to do the following, right? So we need to basically we have the target and we have the control. Now the question is, what are the two things that can happen, right? So, what if we don't have? We'll just split it in cases, then we'll see if we can merge stuff. If we don't have any branches, then I guess what we have to do is look for two things, right? So a node in the control, a node for the control qubit in state 1. Yeah. A node for the control qubit in state 1, right? And then basically apply. And then basically what I need to do is I kind of need to kind of copy all the. It gets tricky because we already need, I think, hyper edges in this case. Because what if we have multiple? What if we have multiple nodes for the target qubit? We need hyper edges already. So exactly, yeah. I mean, a hyper edge. I'm going to just represent a hyper edge as a collection of nodes, right? But I need to reference those nodes somehow, and I think that's what I'm missing in here. So, well, I'll just use the index, right? I'll just use the index. So, yeah. So basically, the edges will just be collections of like tuples or collections of arrays that have like the qubit and the node in the qubit. Yeah. I mean, we could do this more efficiently, right? We could just implement these in a matrix probably, and that would be more efficient, I guess. Well, no, because then you wouldn't have the possibility to have variable length in here. Yeah, well, of course you can. It's just not a matrix, but like an array of arrays. That's it. Just have that implicit as well, as in qubit 0, qubit 1. It doesn't have to be a dictionary. Why do I need it to be a dictionary, to be honest? It can, yeah. Actually, let me refactor that. It's going to be easier. So it can just be, yeah. It can just be like that. I don't need these to be like, and let's start. Let's do this correctly. Okay, so let's start with just one node at each. Okay, so we want one node at each. That's the only thing that we want, and so yeah, that's basically that's what we want, right? So this is just the index. So we want qubit 0 and we want qubit 1. So that's going to be easier to make. I think it's going to be easier to manipulate. So yeah, okay, cool. but nodes and edges make sense. So what the edges will just be basically arrays of like, so this is going to be the qubit and this is going to be the node, the qubit index and the node index within the qubit. And it's going to be basically a so an array of these guys, right? So cool. Good. And so we need to look for a node. We need to look for a node that is. Actually, we need to do this for every node. To be honest, it's not that we're looking for a node. We need to iterate over all nodes of the Q. Oh, okay, so we need to iterate over all nodes of the control qubit. That's the first thing. Now, it's good. Different things will happen, right? So if a node is just one or zero, well, the first thing actually it's easy. So we need first we need to create two edges, right? That's one edge for the control being 0 and another edge for the control being 1, right? And so yeah, I guess if a node is just 1 or 0, and we need to create two edges per each node. I know that might just make no sense, but I think that's just the most generic way to implement that. So for each node, we need to create two edges. Then, if node is just a 0 or a 1, it's the easy case. So we basically, what we need to do is we need to duplicate the target nodes, the target qubit nodes, and apply gate to half of them, right? Exactly. And populate the edges. So that's the easy case. Exactly. So else, so now we need to split the node. Split the node, which kind of means basically we need to take a look at the node and split it right into its 0 component and 1 component. The question is, we're probably going to assume it's always a 50-50% probability for now. We'll see how. I need to understand. I don't know how like if it's not in a 50-50 superposition, how do we keep those probabilities? Like where do they go now? They should maybe somehow be associated to the edge, but I'm not so sure. Maybe because it's like, I don't know, should we keep them? I don't know if they. I don't think they should be still. I don't think they should still leave in the in the new nodes like that we're splitting. That's the problem, because each branch is essentially a system. Like it's essentially a standalone system within the whole. Yeah, within the whole thing, right? So it's or a subsystem, right? Yeah. So split the node, and then basically. Or it's easier, we just say, if node in superposition, then we split the node to do what do we do with the props, and then we just go ahead and do that, right? And like we just duplicate the target's qubit node, blah, 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 and yeah, and we populate the edges. I think that's basically the way to this. So this is where complexity gets in, like hits us hard in this type of model, right? Because for every control gate, you're doubling the amount of nodes that you have on the target side. And when we go to like multi-control gates, like for hyper edges, like so for more than 2 qubit systems, then that's going to get messy because we're going to basically if we have more controls, then well, we don't have to create 2 edges. We're going to have to create like 2 to the power of n edges. Here n equals 1, right? N equals 1, which is basically the number of control qubits. Yeah, so I think that's what we should do. Let's try and code that. Okay, so it shouldn't be complicated. So okay. So what do we do with branches though? If there's any existing branches, let's if we have an existing branch, right? We might have to split branches. Because if the control is part of a branch and the node is in superposition, then we have to split the branch. That's problematic, yeah. And what happens? What happens if probably I'm thinking too much ahead, like as in like with 3 qubits you can have, so with 3 qubits you basically can have the following, right? So let's open Quark quickly. So you can have with 3 qubits you can have these, right? So now in here we have like 2 branches. So what happens if I now do these, right? I'm creating 2 more branches. The question is, are they should be independent from these ones? I know they're not anyhow nested, I think, right? So what we're saying here is we're saying the branches that we have is well, it's either if we just focus on the top 2 qubits, it's the branch 0, 1, 0, 0, and 1, 1, right? Now we have this system in here, and so what this is going to do is it's going to okay, so I think what this is going to do is it's going to say take the control, split it, and you basically find the 2 nodes, right? There are 2 nodes now for the qubit in the middle. So we have 1 node which is a 0 and 1 node is a 1. And so what would happen? Would we duplicate those nodes? I think what happens is effectively a duplicating these nodes within the branch. But then that would be interesting. That's an interesting that's an interesting case. But I'll leave that for later. Okay, so here, although I'm gonna have here the similar issue, right? Which is like, what do we do if I have these operations, right? Like, what if I now do like that? So, and I have a control on a node that it's so there are 2 nodes, right? Okay, but they're not split, those nodes. But what if I do these? So what if I do these? This is another tricky case, right? So now I have this is the example where I have like a plus and a plus branch and a no, sorry, a 0 and a plus branch and a 1 and a minus branch. And now I go and I do these, right? Where does this take me? So this, how should I proceed in this case? So I should go through the nodes, through the target nodes, which are basically superpositions. Okay, but they are within one branch, because yeah. The problem is when we have a third qubit that it's in none of the branches, and I don't know how, I'm not so sure how to treat that. So we have these, and what we're going to have to do is we're going to have to say, okay, so split that node into two, but it's still the same branch, right? I hope we're not going to have nested hyper edges. That would be nasty. Or maybe not nasty. Why? I mean, you can have definitely a nested hyper edge. It's not a big deal. So you would split those two, the two elements, and then kind of, yeah, inside there's going to be just one target element. I think it's always the same logic. It doesn't really matter. But we can try, because then if we can figure this out, and then with 2 qubits and at least work on a way to translate these, I can at least prove whether that makes sense, whether I get the same state vector, right? So I can at least then test that. So I think let's for the moment, like maybe we just need to ignore these. I'm gonna have to ignore, or just ignore for now. So first, let's iterate over all the nodes, right? So we have. I'm basically going to just kind of, do this in here. So I'm going to say for, maybe I shouldn't call this state, but I should call, yeah, I should call this nodes maybe. For node in nodes and basically the control, right? So we're going to go through all the nodes of the control qubit. And we don't apply any gate. What we do is we are going to create 2 to the power of n edges. We're going to first just create like a edge 0, it's just the edge 0 as an empty array, and the edge 1 as an empty array. So this is these. And now what I need to do is okay, so if, and I am in for node, why didn't this get copied while I'm in? Oh, what's wrong? I have one of these mess. Come on. Sometimes the keyboard just does this. So what I do now is like, okay, is the node in superposition? So if the node is the node, right? So the node is already where do I have it? The node is already like the array, right? So if node, what's wrong? What is the, I think it's these. Oh yeah, I had like this insert kind of thing that just eats up the next character. So if node 0, if node 0, so we want to look for zeros. I know there are complex numbers. How do I compare complex number though? NP compare complex number. NumPy maybe I just have to have the 0 as a D type, and then Python. How do I compare complex numbers in Python? Okay, just like converting X into okay, so just like that. Okay. What is this? Okay. But that's not NumPy. That's CMath or whatever. Come on, Python, NumPy. Compare complex numbers. Can this just work? Why is this getting so slow, everything? Yeah, maybe I need to compare the imaginary and the complex arguments. That's it. Emag and maybe that's how I need to do that. Oh, come on. Yeah, exactly. But comparing their modules. Okay. Yeah, and I think I'm just gonna compare. I'm just gonna compare the two components. So is it like, yeah, NumPy real and NumPy emag. So what I will just do is I'll say if node 0 real equals 0 and node 0 emag equals 0 and node, oh, wait a second. No, what am I doing? So each node is an array. Yeah, exactly. So it's the 0 component and the 1 component. They're both complex numbers. So I'm trying to check if either I'm trying to check if one of them is 0. Like these, exactly. So if these are the same thing, but just with node 1, right? Yeah, I'm not a big fan of, like, I don't know how to indent these in a nice way. I'll just do it like the ugly way. I know that's not the best way to do things, but at least it doesn't look the best. So if either the 0 component and 1 component are 0, right? what it means is like no superposition, else we're in the superposition case. So what we want to do, sorry. So if this is not 0 and this is not, what am I doing? I'm so stupid. The just basic Boolean algebra. I think that's correct. Okay, the not there should also be correct, but like, so what I'm saying is, okay, if one of those, and this is the superposition case, because that's what I wanna get. So if, so if one of those is 0, this will fail in the case of where both are 0, exactly. So, and I keep forgetting. So we're in the real and the imaginary part. That makes sense. So this is one number. So we want this number not to be 0 for the 0 component. And we want this number also not to be 0. So this means exactly. So this means both the 1 component, the 0 component, and the 1 component, they must both be non-zero. I think that's correct. So now we need to split the node, right? And so we'll do this. So to do a superposition case, and then otherwise, what do we need to do otherwise? So we need to take, we ignore the probabilities for now, and so we need to duplicate the target qubit nodes, right? So what we have is we take the edge 0, but still I still need to know in which case are we, right? Are we in the case 0 or in the case 1? If we're not in superposition case. So I think I might still have to do the else, because else, so if it's, maybe let's do it like that. So amplitude for the element 0, amplitude for the element 1. So what we want to do here is this 0, right? So can I just take the square? Like, can I just do like, actually, can I just do both numbers and square them, I think? Because actually I can just do like, to be honest, so I can just do the real part squared plus the image part squared. And so I think, I mean, this is going to give me like, the positive of each, and I just sum them. And well, I want to know, like, the only case in which this will be 0 is if both components were 0, to be honest, right? Because I'm getting like a positive number. So I think I just do that, right? And so, yeah, probably there's a better way, just doing the absolute value or something. So basically, what now this is, what it's just saying is, you know, if the amplitude squared of the 0 component is 0, then kind of we have the one case. That might be just overdoing it, but L if, is it like L if or else if amplitude of 1 equals 0, then we're in the case of else we're in superposition. So the only thing I need to do is I need to kind of I want node 0 and I want node 1, right? So I want to have these nodes in here, which are basically which are basically empty for the moment. I'm not sure. And if so, what I'm just saying is that okay, so so if the amplitude square of the 0 component, then we have that the node 0 is node, and we don't have a node 1, right? So we keep it empty. So exactly. So we keep these empty. In this case, it's node 1, right? And in this case, we just need to split it, right? So we want both node 0 node 0. Well, to be honest, like in this case, actually this node is literally like I'm literally creating 2 new nodes in here, and I have to delete this node from the list. Ugh. So I'm literally creating like the node 0, which is like that, and the node 1, which is like that, right? And what I have to do now in all cases is I actually have to delete node. So I need to delete node from nodes. I need to kill that. So maybe what I should do is, you know, a trick would be I set node to be like empty, and then I have a function that just cleans up the garbage. I could do that. I think that's yeah, maybe that's one way of doing it, right? Or remove element from array. Maybe there's a smart way to do that. This is NumPy. Delete. But I guess I can delete while I'm iterating over it. So oh, you give it the index. Okay, so give it the index. Okay, so there is actually these elements. So what I need to do is index delete none, and so what I do is index delete equals. Yeah, well, I need to delete. A second. I need to delete everything, to be honest. Okay. Yeah. I'm deleting the whole. So new nodes. It's like a whole new pass, right? So what I'm doing is new nodes. So I'm just doing now new nodes. Only so only if the length of node 0 is bigger than 0, right? I do new nodes, append node 0, and I do the same for node 1, right? I'm bad at programming, so this will definitely need to be optimized, and it's not efficient or whatever, so there's no problem. So what I'm doing is essentially creating a new list of nodes with the new nodes in here, right? That's at the end, but now I still need to, now kind of add these things to the edges, right? So I have the edges, and what I do is, of course, in the edge, so what I do here is I add this node to the edge. I can do that already, actually. Append node. I append I can also do these at the end, like here, right? Okay, but let's just do it here. It's a bit more clear. And here I do like the H0 and the H1 node 0, node 1. I think I could just put those things in here. Yeah, it's probably better. Actually, then we just append it. Yeah, that's better this way. Okay, cool. So what we need to do now is we need to work on the target qubits. So regardless of these, so regardless of whether we have like one node or two nodes or whatever, I need to take a look at all the nodes. So target for the 0 branch, target for the 1 branch, right? And what we need to do is we need to fill this out. The target for the 0 branch is like, it's basically actually these, right? So it's just like saying for the target qubit, take all the nodes, don't do anything to them, okay? And for target 1, well, it's kind of like saying, well, I don't like that I'm nesting, but like for node, no, not node 1, for n and these, right? So we iterate over all of them, and I'm saying, so what we're saying is for all the nodes in target 1, append, and we're just appending these, right? So we're saying, oh no, this returns a system. Oh, okay. I can just I can just reuse these, but it doesn't matter. We should make a function so I can reuse it, but otherwise I'll just do for each node. New states, new state. So I guess that's it, right? So I'm saying take n, it's the node, apply the gate, it's also called gate in here, and that's the new node, and then append the new node to target 1. Exactly. Yay. And so at the end, regardless of these, well, not regardless, but like if we've got this branch, then we also, so what we should also do is, no, not here. So we should also append target 0. And here we should append target 1. Okay, cool. I think that does the job. I'm not entirely sure. Let's test that, but I think that does the job. So let's just recap for a second. Populate the edges. I mean, I need to return the system and all that stuff now. So I'm here, and I just say basically that. So what are new nodes actually? So for each node, we're doing these, and what we have here is we have. New edges basically is what we have to populate. So we have new edges and new nodes. New nodes I'm already populating, and new edges and edge 0, new edges. Append edge 1. So we have these edges, and so what we need to do is those are totally new, right? So I'm gonna be just replacing. Now here's where this comes into consideration, right? Like whether we have any, should ignore this for now. Do we have any existing branches? Let's assume we don't have any existing branches, okay? Then we'll deal with these. But basically the system, what the system should do is, well, this takes in a system as well. Okay, so we just basically do, so what we'll do is, this is for the target key, for the target qubit, right? So what we're doing, new nodes, because new nodes for this specific target, right? I think I have to make a difference between target 1, target. Okay. Target 0 are the nodes that go in target 1. So these two like replace the target nodes exactly. They replace the target nodes, and new nodes is basically the new controls, right? So what the system is supposed to do is that for the control, we assign the new nodes. For the target, we assigned basically target 0. How do I concatenate that? Is it just the plus function? The plus function? Can I just use that? Because I'm not numpy concatenate. Yeah, but these are not numpy arrays. Maybe I just should do that. Though concatenate. Python lists. It's just with plus. Yeah, I guess so. So target 1. So that's what we're doing, and then return the system. So it affects the controls and affects the targets. Oh, and the and new edges, right? So what we need to do is we need to take the system and say, well, edges, and I'm assuming here that we just kill all the edges. So we just replace all the edges in the system. There you go. So I think that should do it. Now, am I sure that this is doing what I want it to do? So I'm not sure about this case. Now let's test it. Let's test these. Okay, so we apply a Hadamard gate to qubit 0, and now we want to have a control gate. So we want to have, because we know now I want to do apply the control gate on system 2, and then what is control target and gate, right? So the control is the 0, then this is the 1, and then this is the NX gate. Yeah, that's definitely not gonna work. What else if? How did that else if? Python else if. Oh, it is indeed elif. Okay. It's elif. Okay. NP is not defined. Yay! Let's see what happens. So key is not defined. Okay, where? Oh yeah, well, it's control. Target is not defined. Target, awesome. Target. Okay, interesting. Edges. So we have some edges now. So what do we have here? So we have 4 nodes. How can I print these nicer? Have a better way to print these. So print system. Print graph, okay. And so this is the graph. I'll just print hypergraph. Is there a way to do this visually already? Python print pretty hypergraph. If I have the nodes, I don't want to install anything, just maybe matplotlib print network. Graphs in Python's print hypergraph. Maybe I should just. How does this work? PyGraph. PyGraph. For now, maybe I should just. Oh, neat. Okay. Link. Add nodes. No, whatever. I'll care about these later. So let me just just quickly. So first of all, we'll print the nodes. So for node in, why is this 4 red though? Okay. For node in for qubit in system nodes. Print. So we're going to print qubit. What is the, how do I get the index? Python iterate get index. Isn't there like a way that we just, I think, look with indices exactly, with indexes. not like these, not like that. For colors in color, spring color. What if we want that for range? Both index, okay, so enumerate. So I can just use enumerate num name. Okay, yeah. Enumerate. Okay, so I can just say enumerate system nodes, right? And then we get like index. So we get the qubit and the nodes. So print qubit. Print qubit. I'm stupid. Qubit. Cool. And now I say that basically, so for each, now just copy for node in system. Node. So that's the stupid. Qubit. Exactly. So for node in system qubit, and now just basically, you know, print. So I just print the node. Okay, so print node. Cool. So that that's why it's red. So just print a node, and then for edges, we just all we want for edge and E for index and E, whatever for E and then the actual edge, right? So what we want to do is print edge E, and then just, well, edge is just. I think I've done a mistake here. So the edges should just be indexes, not like I'm appending the dem nodes, and that's wrong. That's the wrong thing to do. So we have the nodes, blah blah blah, and then the edges. So we have edge 0 and edge 1. So append, not the node 0. Okay. The thing is, I don't know what indexes these guys are gonna have until I append them, right? That's the problem. So I just okay, for the moment I'll just keep it like that. I'll change these. I want in edges just the indices, not the full nodes, but it can be nice to see right now. So for each edge, so edges for each edge, for each node in exactly, we print the nodes. Print system, I'll call it. Print system. So if I just do this, print system, well, I probably should have executed it like that. Come on. Can I cast this to string, something like this? Or what's the way to do that? Oh, there you go. Okay, so what do we have here? So we have 2 qubits, right? Each qubit is in the state. Why is this array and that's like that? I don't know. Yeah, should probably. Okay, what's in 0 and in 1 state? What are we doing here? So we're doing. I'm not so sure that's the correct thing to do, but so we have 2 qubits. Each qubit has 2 nodes. What's wrong with qubit 1 though? Oh, wrong. That's the way this should look like exactly. So we have 2 qubits. So the first qubit is in the 0 state and then in the 1 state. In the 0 state and the 1 state. Why? That's wrong. No, that's correct. The first edge. There's another mistake here with the. So the first edge is one connecting the 0 with the 0 and the one with the 1. That's correct. Cool. That's what we want. Okay, but I need to give these guys some index and then add the indexes to the edges. So that seems to work now. It seems to work. But why is it like an array of an array added to the edge in here? Node 0, it's an array, it's an array. Where else am I creating something unnecessary? New node. Append target 1. So node 0. Oh, okay. New nodes. I think that's basically I should just NP array. That's how I should. I think that's what I should do is NP array of the node. Is it what I'm no. Because that's edge append. It's the target thing. We're attaching the new node, which is the gate, and N, which is target node, target 1. So where I'm appending to the edges is node 0 and target. So target 0 and target 1. This is the problem. Target 1. Yeah, I think this it's got to do with the plus in here and the fact that okay, I can debug that later, it's fine because I'm running out of time now. But okay, so I got a baseline implementation for the controlled gate. Now, so these I'm basically getting rid of. This still bothers me, so I don't know. This doesn't contemplate this case yet. This doesn't contemplate this case yet. Cool. But we'll do this in the next session, I guess. At least it's doing this. So I gotta do basically to-dos. So to do edges, right? Use indexes. I don't know how you write that. To do implement case where branches exist. to do fix nested array problem. Awesome. And I think I can just I can just basically say conda activate. Oh wait, sorry, conda activate, yeah, because that's another shell, but it doesn't really matter, does it? Oh, what am I doing? Conda activate ehssim. Or is it because it's activated in the other terminal, but I don't know if the terminal where I have the Jupyter thing. Ah, okay, it's there. So workspace, and now I do git status, and basically I add the whole thing. Git commit first version of my apply control gate v1. So yeah, okay, push, and there we finish. Cool.